some of the issues and the challenges when working through quantum simulation. First, you would like to have, in principle, the knowledge that you can do the simulation. And the way one approaches this is to define the problem by saying the goal is to simulate some Hamiltonian we'll call the H-cis, which would be this large Hamiltonian over here. But you're given a different set of Hamiltonians, not just one Hamiltonian, but a whole family of them, which will be the Hamiltonian of the quantum computing units, like each of the gates or each of the subsystems, and you can turn them on and off at will. Then the question is, in a mathematical way, for this in principle issue, whether or not HKQC can generate H-cis. Mathematically, this is a beautiful group theory question about whether the algebra of H-cis is spanned by the algebra of H quantum computer. And I won't go into that because it's fairly simple to do, and leave that for you as an exercise. But this is the starting point for quantum computation or quantum simulation. A second idea and issue is how does one transform this kind of a set of Hamiltonians into the system that you would like to simulate? And one of the earliest approaches of this is to use analog techniques. Which go under the name, for example, of analog deformation. And that is that you might have a quantum computer simulation Hamiltonian, which has a number of terms. And your strategy would be then to manipulate these, deform them, to make this Hamiltonian look like this one, for example, in a time-averaged way or in a stroboscopic way. So, for example, at every time capital T, 2t, 3t, 4t, and so forth, you would like this Hamiltonian to equal that Hamiltonian, not at all times. And this is the strategy and approach, for example, employed by ultra-cold atom gases, Bose-Einstein condensates, when they're being utilized to simulate, for example, a superconducting system. And that naturally works out in many ways because they can be controlled to have similar Hamiltonians. And the Bose-Einstein condensate is very controllable, and you can get an equivalent lattice spacing that's much larger than the physical lattice spacing of atoms inside a superconducting solid. And so you can engineer the kind of Hamiltonian you would like your quantum computer to simulate in many rich ways. So this has been a very effective and useful approach. Here's another idea and challenge, though. Even if you can simulate, so this is in principle, this is one method by which you can simulate, you're still faced by a rather annoying and pressing challenge question, which is what to measure. Even if I just tell you, you can simulate, so if I say you're given some state, which is e to the minus iht times some initial state, if you measure this, it collapses. And then you get only one statistical sample of that wave function. Does that tell you what you want? Does that give you an actual output? And what are its statistical errors? Because after all, nothing is real unless it's reproducible. And in junior physics lab here, those of you who've taken junior lab know nothing is real unless it has an error bar. You don't get an error bar from a single instance of something. But if you have to repeat this many times, your errors now normally, if they're just law of large numbers distributed, going to decrease as the square root of the number of tries. And that often isn't good enough because you don't want to try an exponentially large number of times. But naively, this is what you would have to do here. So maybe what you want to do is not to measure the state. Maybe what you would like to get is some expectation value of some operator. And maybe it's going to be easier to measure that operator than it is to, say, get all the coefficients of a wave function. But even this is fraught with difficulty because it still has the statistical randomness that we just described. So this is an issue of precision. And I will try to illustrate this issue with the Grover algorithm simulation topic that we'll come to in 2 steps. And then let me leave you with one more issue and idea, which is, and this is kind of outside of the scope of quantum simulation of quantum, but it is a very real one for quantum simulations. Instead of building a quantum simulator, why not just improve your classical simulation of the quantum system by using a better approximation? And this approximation might be a quantum-inspired approximation. And this actually has happened over the last decade or so. A whole variety of new approximations have come because of quantum computation that allow you more efficient classical algorithms. And these have swept through condensed matter theory and are now entering into the realm of quantum chemistry, and they go by a variety of names. The technique that started all of this in physics was the density matrix renormalization group idea, which was awarded the Nobel Prize, Ken Wilson and company. But now we have many more advanced techniques, so not just DMRG. And I'll toss out a bunch of acronyms here for those of you interested in this, but also things like PEPS, MIRA, and all sorts of things. You know you're entering chemistry when all you see are acronyms. But these are real ways of getting very useful, highly accurate approximations to answers that you want to find in quantum chemistry.